Let's wait for a couple more minutes. Looks like people are still joining. Okay, let's get started. Hope you can hear and see my screen clearly. Uh, Good evening and welcome to the week 2 live session for the CS104 course. Let's get started. So hope all of you were there for last week or you watched the recording, but in case you didn't, I'll just give you a quick overview of how this works. So we have 2 live sessions per week for this course. One is on Monday and the other is on Sunday, and both will be 1 second, people are still joining. Yeah, so both are meant to help you with problem solving, and they will be in this live session we will align it to the that week's course content from NPTEL, right? So I expect you to have watched the lectures and tried to have solved the assignments. Again, we look at some very similar problems which will help you solve that week's assignment questions if you haven't already been able to do that. And we will take doubts and questions that you might have from that week's course content. And since there are a lot of people, we will have all interaction through the chat box. So feel free to post a question or doubt anytime. I will either answer you right away, or if we have a time constraint, I might get back to you in the next session. But I will definitely answer your question. So feel free to ask. Yeah, and post the session you will be getting access to the slides and the recording for these live sessions. These will be shared by NPTEL. I'm not sure if you've yet gotten last week's slides and videos, but you will get that, and once that is shared you can use the same thing for all the live sessions. Okay, moving on. Yeah, and we'll briefly keep it to 3 parts, right? One is a recap, and then problem solving, and then doubts. and like we did last week, we will take a 5-minute break around the 8 o'clock mark. And always feel free to interact, because that's the point of these live sessions. And if you want something slightly different, if you want a little more recap or a little more understanding of concepts, feel free to suggest that at the end of the session. We can see what we can do about that. So this is all I had on the logistics. For anyone who joined today and is still unclear about any of these things, please ask your questions or doubts on the chat box now. I will wait for 30 seconds before moving on. I think the course enrollments are still open, so I understand some of you might have just joined or might have come to the live sessions this week. So any questions on the logistics, any doubts? I'll give you 30 seconds and then we'll move on. Okay, that's an interesting one. What is this course about? So I'm assuming your question is after having seen the syllabus and having enrolled to the course. So I will assume that and answer this question. So last week we did a kind of brief setting expectations for this course. So this course will not get into the theoretical aspects of AI. It will be a little bit of AI, a little bit of systems and optimization, and how do you efficiently, people are still joining, 1 second. Yeah, how do you efficiently deploy, either it could be inference or it could even be training, right? So how do you efficiently perform AI, which involves a lot of knowledge about the system level fundamentals, right? It could be something like architecture, it could be containers, it could be virtualization, it could be a lot of things. So we are looking at, and we look at some applications of AI. So this is a very practical, hands-on sort of course that is meant to help you with optimizing and accelerating AI workloads. It's not a theoretical AI course, and so it will not go too much into models or algorithms or data sets and things like that, right? Things that you typically expect from a theoretical machine learning course. This is more, as the name says, it's about accelerating AI workloads, and it's about various applications. Hope that answers your question. Any other questions before we move on? If not, let's get started with some of the questions you guys asked last week, right? Will there be any exam on programming? No, like I said last time, I think I am not from the NPTEL team who's actually involved with setting question papers and things like that. But based on other courses that I have assisted with, the exams are typically MCQ based, and you can ask this on the forum or the Google group, right? Where the official TAs who are also involved in setting the question paper might get back to you. Recordings of the previous sessions, there has been only one other week, and the recordings are uploaded and they are on YouTube. If you haven't gotten the link yet from NPTEL, you should be getting it sometime this week. But yeah, all of them are recorded and they are available. It's just 1 week, last week's sessions. Any other questions? Okay, if not, let's move on. Yeah, so last week we saw that some of the references were research papers, and I had asked if you guys are familiar with reading research papers or you would like some explanation on how to read a research paper, right? So today we'll kind of go over like a 3-minute overview of how you read a research paper. So typically if you've opened some of the references available in the slides, you would see that they have papers which are anywhere from 10 to 12, 10 to maybe 15 or 20 pages, right? So it might seem very daunting to read a research paper. So this is an approach called the 3-pass approach, which helps you parse information in different readings, right? So typically what you might do is you might read something from start to end, and that works very well for certain kinds of reading. But with papers there is a lot of dense so please post your messages on chat. Since there are a lot of people, it's difficult for me to trace raised hands and then unmute you and do all that. So please post your messages on chat if you have a question. Yeah, so we'll continue. So with a research paper, you might need to take more of an iterative approach where you read it in iterations, right? So this is a very famous approach, and the link to this is also given in the slide, so you can go and look at it later. So the idea is that you read it to a maximum of 3 times, right? So the first time you read it, you're supposed to get a general idea of what the paper is about. The second time you read it, you are supposed to understand most of the contributions and content of the paper. Now the third pass is a lot of fine-grained implementation details or experimental details and depth, or maybe proofs if you're reading a theoretical paper, and that's not always necessary. So for the purposes of this course, the first and the second pass will definitely be enough, unless you are a researcher working on that same topic and this paper is something that your work crucially depends on, which I think 95% of you wouldn't fall into that bucket. So the first and the second pass should be enough for you. So what do I mean by the first pass, right? So this should take you anywhere from 5 to 10 minutes depending on your reading speed. So what do you read in this first pass, right? So you read the title of the paper, you read the abstract, which kind of summarizes everything about the paper. It says this is what this paper is trying to solve, and here is what we implement to solve it, here are our results, right? All that is summarized in the abstract. And then also read the introduction of the paper, which might be anywhere from half a page to 1 page. So this should take you less than 10 minutes, and the goal of this first pass is to understand what does this paper do. Is it something that theoretically proves something? Is it something that takes an existing concept and maybe implements it more efficiently? Is it something that measures performance? You kind of understand, right? You will know what type of a paper this is, and you'll also know what are the main contributions of this paper. So this is the first pass. So don't read the full paper in this first pass, read only these things. Then the second time you iterate through it, it could take you 30 to 45 minutes. So I've put 40 minutes. Here you could read through some of the related work section, which talks about what are other papers in this area. So it might say paper 1 has done this part of the work, paper 2 has done some other part of this problem, but neither of them look at this particular problem, which is what we try to solve, right? So it gives you an idea of the whole area as such. So related work is that. Then you can also go through the implementation and the results section. So here again a key idea is to pay attention to figures or diagrams that you see, right? For instance, you might see a system architecture diagram which will tell you about the implementation, or you might see some figures or plots in the results which will help you understand the results more. So again, pay attention to all of these things, and by the end of the second pass you should be able to summarize the paper. So imagine you had a friend, right, and explain this paper to them in 10 minutes. You should be able to talk about the paper in that level of detail, saying this is what the paper does, and here is how it does it, and here are the results, right? So if you do these 2 passes, for the purposes of this course, you've gained enough understanding about the paper. You can skip the third pass where you read everything in very, very fine detail and try to understand all of it. And remember this, in the second pass there might be some details that you read and you may not understand. That's okay, keep reading. Sometimes you might want to look up some terms that you don't understand, make a note of those and then move on. But if you don't understand something, don't get stuck there and stop reading, right? Try to understand the overall idea, the overall results, the overall contributions. So this sort of spending this 30 to 40 minutes on a single paper will give you will help you go beyond the contents of just the slides. And again, like I said last week, this is not a mandatory thing, but it will be useful for you if you are trying to actually learn more about what this course talks about, right? So that's one thing. We have a question, let me see what that is. Is it useful for a BSc Math student? That's really your call, right? What exactly do you want to do either in your course or after your course, and how does this course fit into those plans? That's a call that you need to take. I've told you about the course, so think about where it fits in the overall scheme of things for you and then make that decision. It could be useful to anyone, right? As long as that someone is planning to either work on this or take up a course on this or get a job in this field or whatever. So that's up to you to decide. Okay, so this is about reading a research paper. Let's move on. And if you have any questions in any of this, ask on chat. So coming to the other thing that was asked last week is the basic terminology about GPUs, right? So for instance, you might have heard of SPs or SM. So guys, try to join within 2 minutes of 7, right? I can wait 2 minutes for people to join, but waiting 10 or 15 minutes is not practical, and it's also disrespectful of others' time, people who joined earlier. And it keeps disrupting the flow when I see people joining and I have to approve their entry. So please try to join on time. And we will end on time as well. I don't intend on taking more than 2 hours of your time. So it would really help if you joined on time, and then we'll wrap up on time. Anyway, getting back. So SM stands for streaming multiprocessor and SP stands for streaming / scalar processor. And this is what people normally refer to as a CUDA core. So you might hear things like, oh, this GPU has 1000 CUDA cores or 2000 CUDA cores, right? So what they are actually referring to, the technical terminology for that is SP. And each SM typically has multiple SPs. So you could see, I think in your own this thing, right? We see examples where you see different. Here, for instance, you see that there are 5000 SPs overall, and we see that there is 6912 SPs, right? So a lot of these different GPUs will have different number of SPs per SM. So the total number of CUDA cores would be the number of SMs into the number of SPs per SM, right? That's how you get that. Yes, we do have recordings available. If you haven't already gotten that link, you will get it shortly. So all of the lectures are on YouTube, so you can watch it later. That's not a problem. Yeah, so this is basic terminology, and newer generations of GPUs also have, you're welcome, also have tensor cores. And we will not go into too much detail about tensor cores here. I think in the later lectures where we talk about mixed precision, we will get into the details of tensor cores. So for now, just remember that in general, there is what is known as a CUDA core, and there are also what are known as tensor cores in the newer generations of GPUs. And the other thing to keep in mind is that a lot of courses or a lot of literature that talks about GPUs typically talks about NVIDIA GPUs. But remember that they are not the only hardware vendor of GPUs, right? There are a lot of other companies too, for instance AMD. And in the embedded space, there might be other companies as well. For instance, Mali GPUs that you might see on phones. So a lot of things that you learn, including such terminology, might be specific to an NVIDIA GPU. So always try and understand what is the meaning of those terms rather than just the name of those terms. Because when you switch to a different hardware vendor or a different architecture even, some of these terms could change, but you'll see very similar meanings for those different terms. So keep that in mind. And coming to the memory hierarchy, again similar to what you saw on the CPU side, you broadly have a register file, you have caches, and you have global memory. There is a lot more detail to the GPU memory as such, but again for this course it's not very relevant, so we will stick to this much. Later on at some point, if we need to know the details, I will definitely tell you about them. So this is about GPUs in general. Moving on, so there are different kinds of GPUs, right? Last week we didn't have enough time for this, so we broadly said that GPUs for the data center are different from GPUs for the edge. Now what could some of those differences be? Obviously, intuitively all of you have a sense that GPUs for the data center are more powerful than GPUs for the edge, and that is a correct assumption for the most part, and that is by virtue of various things. For instance, you might see a smaller number of SMs or a smaller number of SPs in the edge GPUs, and similarly you might see a smaller amount of memory. For instance, the edge GPUs will have anywhere from 4 GB to say 32 GB of memory, whereas data center GPUs may start out at 32 GB of memory, right? So again, that's one difference. The third difference that I think somebody was talking about last time is power. Typically edge devices are made to be a lot more power efficient or energy efficient because these might have a variety of deployment conditions. Let me just get a pen. Yeah. So for instance, you might put one of these edge devices on board a drone, right? And that drone might have a battery or a power bank powering it up. So that means that you have some limitation on the energy consumption, right? So that's why typically edge GPUs are designed to be more power efficient. So if you look at the data center GPUs or the data center machines, they might consume hundreds of watts of power, but the edge GPUs would be anywhere as low as a few watts, 1 to say 5, 6, and the maximum typically is maybe 65 to 70 watts of power. So this is again another way in which they are different. Laptop GPU is what category? It definitely wouldn't come into data center, and again this edge is a term that is used in a very broad sense, right? So you could call a Raspberry Pi an edge device, you could call your mobile phone an edge device, your laptop is also an edge device. So broadly the term is used to mean two things, right? In the computational world, it is used to refer to things that are slightly less powerful and devices that are placed close to the sensors. In the networking space, it is used to refer to devices that are at the network edge. Both of these are valid definitions, and as a result you have a lot of devices that fit into this category of edge, right? So a laptop GPU could also be called edge very loosely, right? It's not wrong to say that, and it definitely is nowhere near as powerful as a data center GPU. And another final dimension along which edge GPUs are different is their form factor. So although these figures don't show you that, right? If you look at an edge device, so this one for instance is based on I think the Jetson Xavier NX. Sorry, this is a bit blurred, but if you actually look at this edge device, it's probably the size of a credit card, right? Whereas if you look at the size of a desktop GPU, it is much larger than this. So the form factor or the size is also something that's different, that differentiates the edge. And finally, there is one more difference. In case of the edge, all this memory that you see, for instance here you see 8 GB DRAM, this is actually shared. If you see here, there is a CPU here and there is a GPU next to it. So this 8 GB of RAM is actually shared between the CPU and the GPU. It is a common memory. So when you buy laptops, sometimes you would have heard of GPUs on them, right? And those GPUs would have specs saying that there is 1 GB of graphics DDR memory, or there is 2 GB of graphics memory on this laptop. So those laptops and all these data center GPUs have what is called a discrete GPU, right? Which means that that GPU comes with its own memory. So the CPU has some amount of RAM. Most of your laptops, I think, have 16 GB of RAM. Now, if you buy a laptop with what is called a graphics card or a discrete GPU, the GPU has an additional amount of RAM. Typically, that is somewhere from 1 to 4 GB, right, in your laptops. In the data center world, of course, the GPU will have much higher RAM. But this RAM is separate from what is the CPU RAM. It is the GPU RAM itself, right? Whereas if you look at the edge, as you can see here, there is only one DRAM and there is a memory controller fabric, and both the CPU and the GPU have access to this same memory. So this is what is called an integrated GPU, right? Where it also gets the name not because of the shared memory, but because of the way the CPU and the GPU are connected. So if you look at all these data center GPUs, there is what is called a PCIe bus, right? PCI Express, and that's how the GPU is actually connected to the CPU. Whereas here, both of them are on the same SoC, system on chip, and that's a very fundamental difference between discrete GPUs and integrated GPUs. And if you buy a laptop without a discrete GPU, right, then you by default have what is called an integrated GPU. The hardware vendor, for instance, if you buy an Intel laptop, it comes with an Intel integrated GPU, and again that GPU shares the same RAM that is available for the CPU. So these are some of the fundamental differences between GPUs for the data center and GPUs for the edge. And if you use either of these things are important to know. Any doubts or questions so far? Okay, I'm assuming there isn't. So again, so these, I think again someone asked me about this A100 versus V100. Now what you should try to do is to look at these architecture white papers a little bit, right? And again, that's not a mandatory thing, but it's a recommended and suggested thing if you're interested in learning how architecture evolves, right? So Volta was one of the, it's a fairly new GPU architecture, 2017, and Ampere is one of its successors. And after that we have things like Hopper and Turing, right? So look at these architectures, you will see certain things that changed. For instance, you will see tensor cores were here too. So if you're curious, you might wonder, how are these tensor cores on Volta different from tensor cores on Ampere, right? And there is an answer to that, but again, it's out of scope for this course, so we won't go into that too much. But this will basically tell you some high level differences between two GPU architectures, for instance, and these might change, right? The number of cores, the number of SMs, number of SPs, all that might change. And additionally, you will see things, sometimes you might see interesting things like this, a new floating point data type. So for people who are aware of data formats and types, you might know that you would have studied this IEEE 78754 or those standard formats, right, where you are taught FP32, FP64, and it seems like such a fixed and very stable thing. But now you see that GPU is coming with support for TF32, which seems like a very different data type, and later GPUs in fact are looking at things like FP8. I think recently one of the GPUs has support for FP8. So if you look at why some of these features are there, you will realize that a lot of it is very closely tied to AI, right? For instance, traditionally GPUs were used for HPC workloads. I and HPC workloads have this characteristic that they need very high precision. For instance, a lot of them work well only with FP32 or even FP64 formats, right? So GPUs used to support that. But with the advent of AI workloads, a lot of computation works well even at lower precision. For instance, some of you who have worked with inference may have heard of quantization. Some of you might have also heard of mixed precision training. So these are all methods wherein you can lower the precision of the data and you can still get enough accuracy, right? And why is lowering the precision of data important? Right? It is important because you save a lot of computation, so you save a lot of time, you also save a lot of energy, right? So there are all of these new formats coming up. Yeah, bfloat, I think bfloat was for TPUs, but again it proves the same point, right? There are a lot of new data types and data formats coming in specifically for AI. So let's look at the other questions. GDDR6X, yes, that is again GPU memory. So we'll hold on to that a little bit. I think someone asked me about VRAM or GPU memory, so we'll talk a little bit about that when we get there. Okay, GPU can do parallel processing faster than CPU because of more cores, but how is CPU preferred for sequential operations? So basically, if you have something, so GPU is, as you have already understood, GPU is made for massively parallel workloads, right? So if you have something sequential, the GPU is very underutilized. Let's say it's capable of doing 1,000 things in parallel. Now you give it only one thing, no matter how powerful it is, you're underutilizing it by 99%, right? So there is only so much the GPU can do for an inherently sequential workload. And the CPU on the other hand is more general purpose, so it can handle that reasonably well, right? So that's one of the intuitive explanations for why the CPU would be preferred for sequential operations. Hope that helps. So yeah, so you don't need to know a lot more detail about how volta is different from ampere or things like that. It's just again for curiosity. So these are both fairly recent architectures. So looking at features in these two architectures will help you understand how the space is evolving. So take a look at both of these white papers or NVIDIA's blog posts, right? They'll help you understand better. Yeah, and then moving on to DGX, again somebody wanted to look at the architecture a little bit. So if you look here, so this was the PCI switches that I was talking about, right? So if you notice here, there are 4 GPUs connected through PCIe switches to the CPUs, right? And then of course there are network interface cards and all of that. But again, one more interesting thing, you will see this NVLink here, right? So for GPUs to communicate among each other, there are some special high bandwidth, high speed connections like NVLink which are used, right? Again, because that communication needs to be extremely fast. So when your computation is very fast, then your communication can become a bottleneck, right? Because if this CPU needs to talk to this GPU, it has to go all the way through this CPU and then through this CPU to this GPU, right? So instead you have a way for them to directly talk to each other using things like NVLink. So that again helps on the communication front. So if you look at very high performance clusters like the DGX, then you will see things like NVLink or some other form of high bandwidth connections. And again, some of the specs are here. So the CUDA cores it has is 40,000, and you have dual 20 core Intel Xeons, and you have 256 GB of GPU memory, and you have 4 into 1.92 TBs of SSDs, and you have 512 GB of DDR4 RAM. So this is what I was talking, right? So you see that there is a separate field called GPU memory, and there is a separate field called system memory, or more generically CPU memory, right? So here this 256 GB is a total of is across a total of 8 GPUs, which means that it comes to 32 GB per GPU. Yeah, what else? This also has tensor cores. So I think each of these GPUs are V100 based. If they are V100 based, then there are 5120 systems. So 5120 tensor cores. So I think there can be deployments where it is not V100, so then this number could change. But yeah, does it have specific GPUs? I am not very sure. I think there are a couple of variants. I can quickly look that up. I think there were a couple of variants which used something from the Volta generation, and there were others which used GPUs from Pascal, or I don't remember which else, but they don't necessarily have just V100s. It could be other GPUs also. So yeah, and I think I saw a raised hand. So if you have questions, please post on chat. I will answer them whenever I see them. Yeah, so this was one more. Okay, there's one question. Why can't edge device manufacturers provide only GPU instead of both GPU and CPU? GPU can do both parallel and sequential operations. Okay, so the GPU is again a very specific thing, right? For instance, it can do matrix multiplication, but the CPU has a lot of other things that it handles. For instance, here there is a network card connected to the CPU, and there are a lot of, for instance, the OS itself sits on the, so if you think about it, the GPU is kind of like a peripheral, right? Now let's say you have a hard disk. A hard disk is a peripheral. You will still need a CPU, right? Similarly, the GPU on the other hand is not like a storage device, it is a compute device, but you will still need a CPU to do a lot of other operations, right? A GPU cannot be used independently. So that's the reason most systems that you see, even if you buy a GPU card independently, you will ultimately put it along with a CPU kind of thing. For instance, FPGAs are different that way. You don't specifically need something other than them, right? But GPUs, for a lot of reasons, they are specialized. They are intended to do only what computation they are designed for, and a lot of other things are taken care of by the CPU. For instance, here some data comes on the network, the CPU handles it. Let's say you have a SSD, right? So here, for instance, you have some TBs of SSD, right? Now your data set sits on this SSD. So your CPU takes care of first getting that data to RAM. It reads from SSD to CPU RAM, and then it does a copy from CPU RAM to GPU RAM. So in that sense, there are a lot of operations apart from the computation that the GPU cannot do by itself in its current rendition. Maybe there is, if I go beyond exactly what you're asking, maybe there is a way in future that GPUs can evolve to be an independent entity all of their own and do not need CPUs or an operating system and things like that. that might very well happen, right? But in their current rendition, they will definitely need a CPU to handle a lot more than just computation, right? Any workload that you can think of all the steps that are involved in that workload, whether it be deep learning, whether it be a simple matrix multiplication. You will see that a lot of things are done by the CPU that cannot be just offloaded to the GPU. All that can be offloaded is just the computation. Hope that helps, but feel free to look up answers to such questions, right? It's always so when you have an idea, rather than just dismissing it as this is a stupid idea, look at things. And especially in research, you might very well find people who have thought similarly and who tried something like that, and then let's say it has worked, or let's say they found out some reasons for which they couldn't do that. So it's always good to be curious and look up to see whether your curiosity, I'm sure a bunch of other people would have had the same idea. So look that up after the class as well. But hope this helps as an initial answer. You're welcome. Let's move on. Let's see how much more I have from questions for last week. Okay, so moving on to tensor course. Again, I won't go into too much detail on tensor course here, because I think we have a mixed precision lecture which will kind of go a lot more into detail. But here again we have an interesting way of sort of reducing the computation while still maintaining some level of accuracy. And again, this is a very deep learning specific thing, that if you do this for deep learning, then you aren't really affecting the accuracy that much, right? That's why it has found implementation in hardware. So here the basic idea is, so typically what would happen in what is called a MAC, right, where you have a multiply and an accumulate, or very simply a multiplication and then an addition. This forms the fundamental operation in all of machine learning and deep learning, right? So whenever a MAC is involved, typically what you would do, you would, let's say you had everything in FP32, so you would take one FP32 and multiply it by another FP32, and then you would add it with the next FP32. This is what you would do. Now what the tensor core does is it instead takes two FP16 inputs, right? These two, they are taken at half their normal precision, and the product is computed. Now the product will be FP32 itself, and then you sum that up with an FP32 matrix. So your overall result will still be FP32. It is FP32 here, it will be FP32 here as well. What you save on is in this multiplication. Instead of doing FP32 into FP32, you are doing FP16 into FP16, right? And that saves you a lot of computation and a lot of time. So tensor cores are hardware cores that are designed to support this kind of an operation. So DGX1 again has the version with the V100 GPUs have 640 tensor cores, but this is not something that's found only in DGX1, right? Tensor cores have been available from, I think, Volta. So Volta had what was called first generation tensor cores, and then I think Volta, and then there was one more architecture which had second generation tensor cores, and then finally I think the Ampere has what is currently the third generation of tensor cores. So this has been in all these three generations, so it's not some feature that is linked specifically to DGX1. So we will see a lot more about this in the lectures about mixed precision and those things, right? So we won't go into more detail here. And moving on, I think some of you had asked me about FPGA versus GPU, and again this is I've answered it very specifically for AI. and I've put in a link as well from Intel, which is fairly accessible and easy to read. So feel free to go look that up, right? So I've given a few characteristics of FPGA, and all these are in relation to the GPU. So when I say lower latency, it means that FPGAs can give you lower latency as compared to GPUs. Now, what I have not gone into much detail is that each of these characteristics can be traced to one or more architectural features, right? For instance, if I say lower latency, if you go and look at an FPGA, you will see that it has a lot of high bandwidth on chip memory, whereas for GPUs the memory is farther away, right? So you spend a lot of time reading and writing to memory, so that might be one reason you get lower latency on the FPGAs. So that is something that you can think about if you're interested in this. Again, not very mandatory for the course, but since I'm catering to a wide set of audience with varying interests, I always put these things in. It's up to you as to how much detail you go into. So we'll talk about each of these features, right? With an FPGA, something that's always been notoriously hard is that it's difficult to program. So if you've used a GPU, I'm sure you must have, if you have used it, you would have used it with one of the deep learning frameworks, which would have typically been TensorFlow or PyTorch. And at this point, there are enough tutorials on the internet that it's very easy for you to figure out how to implement a simple CNN or whatever model it is using PyTorch or TensorFlow. But the same is not the case with FPGAs. The programming abstraction is a little more low level, and again that goes down to the architecture, right? So FPGA stands for Field Programmable Gate Array. So the way we actually execute on these is by making modifications to the circuits in a way, right? So because the hardware is that way, the programming abstraction is also at a lower level. So for instance, imagine writing, I'm sure all of you have written C programs, at least most of you would have, and you might have also seen assembly level code, right? For instance, you might have used a disassembly tool and you might have seen assembly code, right? So now think if you had to write a C program for matrix multiplication and if you had to write assembly code for matrix multiplication, right? And those of you who have seen assembly code will agree that assembly code is a lot more difficult to write, because again the abstraction is at a lower level. You need to know a lot more about the machine, you need to know a lot more about the instructions, right? Whereas C is very agnostic, right? In a similar sense, when you program or when you write code that's meant for FPGAs, I think this is done in VHDL or Verilog or one of those, it is a lot more difficult, right? That's one thing. The other thing is FPGAs have lower power consumption than typical GPUs, and they are also more energy efficient. And FPGAs bypass the CPU, and and since they are programmable logic, they can also adapt easily to newer models. And in deep learning, there are new models almost every week or every other day, right? So this is something that is in favor of the FPGA. So it can very easily adapt, whereas with a lot of with GPUs, you will see that with GPUs and even more so for ASICs, right? They are designed for certain things. You will find that they are not very well suited for certain other things. For instance, if a newer network comes up with some different operator or a different layer, the ASIC may or may not be able to handle that. And similarly, a GPU may not be well optimized for that. But at an FPGA, since you have control over this very low level abstraction, you can easily adapt to newer models. And again, this is not very necessary from this from the point of view of this course. So I will leave it at this level of detail, and later if you have questions, feel free to get back to me and we can talk about it. Okay. Any doubts or questions so far? I think we'll wrap up the recap in about 5 more minutes, 5 to 10 more minutes. Okay, there are no questions. So next we will move on to a VM. So this is sort of a logical representation of the full computing system environment, right? So like I think I had this slide last week where you saw different abstractions, right? For instance, a simple abstraction is blocks on your hard disk being represented as files, right? So similarly, a virtual machine is also a logical representation of the underlying machine, right? And you do this by adding some layers of software. Now, why is this useful? You could do various things. For instance, a very common use for VMs. So I noticed that a bunch of you have been saying, I have a Windows machine, but all the tutorials and things on this course are made for Linux machines. So how do I need to have a Linux machine? Otherwise, how do I follow these instructions? So a simple answer is a virtual machine, right? You can always get VirtualBox or whatever virtual machine software you prefer, and you could get a Linux system up and going, right? And then you'll be able to follow the instructions of this course exactly, right? So that is one functionality. You could have multiple OSs on one machine, including some legacy OSs. Let's say you have a favorite game that only used to work on Windows XP, and you want to play that game really badly now, but your hardware is no longer having that OS, right? You could have a virtual machine. And similarly, there are a bunch of use cases for it. For instance, you could have isolation. You could have more of an isolation than the typical process abstraction from Linux gives you, right? And similarly, you could have security, you could have platform emulation, you could have some optimizations, lots of things. But this is the broad idea of virtual machines. And isolation is a key idea, right? So typically in the Linux system itself, there is some degree of isolation. For instance, a process cannot access something that is not in its own address space. And similarly, a process may not be even able to see other processes, right? So that is the idea of isolation. But again, like I said, processes do not have a very sound isolation, right? Because they do share some stuff, and this is intentional because isolation and performance is in a way a trade-off, right? What is a process? So if you've studied operating systems, you would have kind of an idea, and for people who haven't, I would recommend looking through a primer of some operating system course slides. But broadly, a process is an abstraction. So if, let's say, you write a program, right? You write a program to multiply two matrices. Now when you run this program, it becomes a process. So a process is typically defined as an instance of a program, right? And it is also the very commonly used abstraction in Linux. So you would have heard of things like process trees, child process, parent process, right? So a program in execution is typically called a process in the Linux world and in the Windows world. It's a very common term. So if you have, for instance, right now you're listening to this call, right? So on your OS, whatever it is, Meet is running as a process. Additionally, you might have, let's say, the course PDF open and you're trying to look through the contents. So your whatever PDF viewer you use is also running as a process, right? Now by definition, your OS gives you some level of isolation between these processes, right? What this process can see. For instance, your Meet application will not be able to see the variables of this process. That is the isolation that the OS gives you. But there is a trade-off that you pay for any form of isolation. So the more you isolate something, you lose in terms of performance. So processes, even though they come with some level of isolation, still share a lot, and this is by design, because the operating system wants to be performant rather than provide too much isolation, because isolation is again a very niche use case. So processes give you great performance, but they are not isolated enough. So one alternative you have is to set up a full system VM, but again, while that gives you great isolation, it is too heavyweight, meaning that you will encounter a performance overhead. So great isolation, too heavy. And why is it heavy? There are again details, a lot of details, but a high level answer is that you have a different OS per VM. So like I said, you might have a VM with a Linux OS, maybe Ubuntu. You might have another VM with some Windows OS, right? So all of those add to your overhead. So while system VMs give you good isolation, much better than processes, they are still very heavy and they come with a performance overhead. So that's one of the reasons why we move towards containers. So containers are somewhere in between. So if you look at, let's say this is processes, this is VMs, or actually system VMs, and this is containers. So containers are the most lightweight. No, I'm sorry, this should be VMs, this should be processes, right? So containers are the most lightweight, VMs are very heavyweight, they add a lot of overhead, and containers provide some amount of isolation, which is better than what a process does, but not as good as what a VM does, right? So but containers is kind of a sweet spot, because it gives you more isolation than a process, but it still remains more lightweight than a system VM. So containers have become the preferred form of virtualization for a lot of use cases and for AI. And how containers implement some of their isolation, that is mostly based on namespaces and control groups. So all these are typical Linux features that containers leverage to have this isolation. For instance, here you see that there are two groups of processes, both running within two distinct containers, right? So these are some of the details. Again, we'll skip that, but remember overall that containers are more lightweight than system VMs, but they give you more isolation. Docker is a container. Again, there are some differences between containers and process VMs. I would have to look that up. Oracle VirtualBox, yes, is a system VM. So Docker is definitely containers. There are some differences between containers and process VMs though. Yeah. Okay, I think that's all I had on containers. So yeah, this is something that again someone had asked last time. So VRAM refers to video random access memory, very commonly called GPU memory. Again, like I was giving you an example, when you buy a laptop, it might say graphics card with GPU memory of so and so. So discrete GPUs come with their own dedicated memory, and the reason is very simple, right? The closer memory is to compute, the faster you can access. So in fact, for people who are interested in memory, there is a fairly new trend called in-memory compute. So a lot of recent work has found that we spend a lot of time and energy moving data from wherever it is to wherever the compute is. So instead, what if you could have the memory be closer to the compute, right? That's the logic. So in-memory computing is one of those newer paradigms that explores this. You can look that up if you're interested. And discrete GPUs like I said, come with their own dedicated memory. Integrated GPUs don't have this dedicated memory. So some part of the CPU DRAM may be reserved for them, and in case of integrated GPUs, that would be what constitutes the VRAM. So let's say you have 8 GB of DRAM. There may be a system imposed upper limit, which I think usually is 4 GB. So the GPU can use up to 4 GB, right? That might be a policy. Again, this 50% might change with OS and with a lot of other variables. This is just an example, right? And earlier somebody was talking about GDDR, right? So again, when people talk about various types of memory, look at what is the technology, right? So you might hear of SRAM, you might hear of DRAM, and similarly you might hear of DDR, and you might hear of different variants of DDR. You might hear of LPDDR. If you look at all these edge devices and what is the memory used on them, you will typically see LPDDR, which stands for low power DDR. And if you look at GPU memory or VRAM, you will see what is called as GDDR, graphics. Again, there are some differences in these things, right? For instance, the GPU DRAM, the GPU RAM has, I think, double data rate. There are some differences like that which differentiates it from the typical DRAM. So we have a question, could you repeat in-memory compute? So I think I'm not too familiar with this, just a disclaimer, but broadly the idea is that you spend a lot of time and energy moving data from wherever it is to wherever the compute is. So instead of moving the data to the compute, you move the compute to where the data is, right? So for instance, let's say you have a RAM chip. So I put some compute onto the RAM so that you don't need to move data at all. You can compute it wherever it is, and that could give you energy efficiency. It could give you lesser time because you're not spending time moving data now, right? So if you think about the whole computation ecosystem, you see that there is this whole memory hierarchy, right? There is SSD, then there is some sort of form of RAM, then there are caches, and then finally there is compute. So if you think about compute, there is a lot of data movement that happens, and depending on the workload, this could actually be greater than the compute itself. So in-memory computing is one of those ideas that explores this. So again, something that's very fundamental, but as people question these fundamental assumptions, technology progresses in different directions, right? So you could look that up if you're interested. Again, not very relevant to the course, but yeah. The PPT will be uploaded. It will not be on the course site, but just how you get announcements about these live sessions, you will get an email giving you a link to the folder where all of these PPTs are stored. So I can actually do that for you if you haven't gotten an email, but you will definitely get one typically, right? And the videos are also on YouTube, so you don't need to worry about that. Okay, I think this was the last thing I had on the recap side. Someone had asked me about CUDA WMAA. So WMAA stands for warp, level, matrix, multiply and accumulate. Again, we haven't spoken about warps, but warp in the context of a GPU is a group of threads that always executes together, right? And the size of the warp might depend on the architecture, but typical warp size I think is 32. And CUDA WMMA is used for tensor core programming. We will not go into more detail here because you haven't looked at tensor cores and you haven't looked at mixed precision and things like that. So we will revisit this if anyone has more questions after the lecture on mixed precision and tensor cores. So with that, I think I'm done with all the questions you guys asked. I have a little bit of recap from week 2 and then questions from week 2. So we are almost at the 1 hour mark right now. So we can take a 5-minute break. Before that, does someone have questions or doubts or anything else that they'd like to clarify? Please ask now. week 1 and week 2 PPT and video link. Yeah, so week 2 is not yet on YouTube, but it will be uploaded after this and it will be shared with you. But week 1, I think I can quickly put the link in case you haven't gotten it. Let me do that before we take a break. So one simple thing you can do is to just look out for this channel, and this channel will be where all the week's videos go. So even if I don't explicitly send you the video links, you can just look at this channel, and I typically upload the videos within a day of the live session. So you can just look out for that, and same for the drive link that I would share. So this would have all the week's PPTs, and typically I upload them within 24 hours of the live session. So you can keep an eye out, bookmark both of these things, and you should be set on the videos and the slides. And again, if you've missed this out, the NPTEL team will share it with you, so don't worry. Okay, let's take a break now, and it's 8:05, so we'll resume at 8:10. Explain support for TF32 in A100. Sure, very briefly, because again I think some of the later lectures go into this, and I will take it up in the next session because I think we already have a lot for this session, but I'll definitely note down your question and cover it. And in these 5 minutes also, feel free to post questions. I will come back and take a look. I'll keep the call running, but we'll resume at 8:10. Okay, let's continue. We have one more question. Can you explain the top 5 error? Yeah, broadly, I'll give you a quick answer now and then a later answer. I typically like to put in a slide on doubts you guys ask because it's useful for you to go back and look at it later and also look at resources that I've linked, right? But the short answer is a lot of these ML models are classification models, meaning that given an input, they try to tell you which class it belongs to. For instance, it might say this is a dog, this is a cat, right? And top 5 error is so a classifier also can give you the top n guesses, right, or predictions that it has. And the top 5 error tells you, it's a metric that tells you how many times the classifier did not include the correct category in its top 5 guesses, right? So it's not just the top guess but the top 5 guesses. For instance, if you gave it a picture of a cat and it told you, let's say the first prediction was dog, the second prediction was elephant, the third prediction was lion, the fourth one was tiger, and the fifth one was snake, right? Cat was not among any of them, right? So that would be an example of a top 5 error, but I'll put in a slide and then I will let you know. PPT is being shared. Can someone else confirm if you can see it? Anyone else, can you see my screen? Okay, great. So Amit, could you please try rejoining? Sometimes Google has that issue where great, multiple people can see. Please try rejoining, and always remember, throughout the 2 hours I will share my screen. So if at any point you don't see my screen, please rejoin immediately or even ask on chat, right? But without the screen, a lot of what I'm talking will not make sense. So please ensure that you can see the screen. Anyway, yes, so I will explain it with an example next time, but hopefully broadly you got the idea. Yeah, so moving on to week 2. So we looked a little more into, so we had an introduction to virtualizations and containers in week 1, right? In week 2 we moved to a more hands-on approach to containers and particularly Docker. So first we learned about version control and again a recap of VMs versus Docker. We looked at the Docker lifecycle. We looked at how do you get images, Docker images from a cloud or a hub, right? And then we looked at how do you use tools such as Jupyter Notebook, right? All of this continued your understanding and application of containers and Docker. Then we moved on to scheduling and resource management. So we looked at the HPC system and how it evolved, and then we looked at a typical scheduler, which is Slurm, and then we tried to understand why Slurm was not sufficient for AI or deep learning, and we looked at Kubernetes, which is an orchestrator of containers, and we learned a little bit about nodes, clusters, pods, and features that Kubernetes offers, such as load balancing. So with that, let's go into the details. So again, like I said, with VMs, you do get isolation, right? So here, for instance, you have 2 VMs, one with an OS Ubuntu, one with some other OS, and you do get isolation. But there is a computational overhead that comes largely from having this full additional guest OS, right? So the OS associated with a VM is typically called guest OS, and the OS associated with the host machine or your actual hardware is called the host OS. So this form of having VMs introduces a computational overhead. So you move to Dockers where you don't have another guest OS. So it is a lot more lightweight and it's not really totally isolated. The isolation still is not very solid, but it's reasonable enough. It gives you more isolation than typical Linux processes. So containers is kind of a good middle ground for us in terms of both performance and isolation, and that's why it's so popular. So with that, looking at the container life cycle, right? So you can create a container, then you start running it, then you can pause a container, you can unpause it, and then when it is running you can also stop a container, and then you can finally delete a container, right? So this broadly forms the container life cycle, and some of this course involves a good bit of hands-on to really understand it, right? So Docker is very user friendly and usable, so I would recommend you set it up on your own desktop machine and try using these simple commands. That would give you a lot more more of a good hold on some of these commands and some of these concepts as well. So again, you could have different forms of AI or hardware, right? So on-prem is something that certain companies might do, where they have many nodes available and many users available. You might also have many users but a single node, which is again an on-premises example. You could also have some form of a cloud or hybrid deployment where you run some things on a cloud, and or you could do some parts in your own on-premises cluster and some parts on the cloud, right? Some form of hybrid. You could also have edge or IoT, and again you could also have some inferencing stack that gives you. We have a question. Textbook, I think I went over this last time. So we don't have a textbook because this is an interdisciplinary subject, right? So for instance, if I were to recommend textbooks for all the things that are covered in this course, it would easily go to 8-9 textbooks. I could give you one textbook for OS, one textbook for virtualization, one textbook for theoretical AI and stuff like that. But this is an interdisciplinary course. So what you can do is to use the references in the slides itself to learn a little more about each of those concepts, and that way you don't need to learn the entire subject to understand what these things are. So typically the slides will come with some references. Make sure you go through those, and that should be enough, right? Yeah, one more question. What is a node, right? So very loosely speaking, you can think of one node as a compute element, right? So let's say I have maybe one GPU, and I can say that's and of course this is attached to, so let's say I have a typical 3060 machine, right? So I can think of this as one node. Now maybe I have 10 of those, that becomes an example for many nodes. So you can think of it as a compute element. I don't want to put a point on it and say it's a CPU or it's a GPU. Depending on the kind of workload and the kind of cluster, it could be either or both. But you can think of it very generically as a compute node. Okay, so here we talk about the difference between orchestration and scheduling, right? So like I said, before AI workloads came in, a lot of GPU clusters were used for HPC, and HPC in those times there were containers were probably just coming up, and so a lot of the schedulers that were designed for HPC was bare metal based, but they do support containers, and again they have no support for inferencing as a first class workload, but they do have good amount of scheduling such as priority queues, preemption, things like that. And again they are very tuned to performance. They leverage your knowledge of topology, knowledge of things like InfiniBand and all that, right? Now orchestration is kind of scheduling with a lot more adaptations, particularly for AI and microservices, right? So again, I don't want to go into too much detail on things like microservices, but broadly the computational pattern changed from a monolithic sort of application to different smaller subunits being handled by different pieces of hardware or different containers, right? So that's the microservice model, and you might have heard of this in anything from websites to AI. And this orchestration is container based. It natively is intended for containers, and you have features like scaling up, scaling down, and it also provides various support for various scheduling features, and it has complex support for complex AI pipelines. And Kubernetes is a very good example of this, right? So orchestration is slightly different from scheduling. It goes beyond what scheduling was designed for, and it has a lot more features like scaling and load balancing and things like that. Now coming to a simple HPC scheduler like Slurm, right? So you have this notion of a controller and you have this notion of your compute nodes. So the controller is like a manager, right? And this is a central entity. There is one manager to monitor the resources and workloads of an entire cluster. So this runs on one particular node, and then all of the other nodes are what you call compute nodes, right? So let me broadly say there are 10 machines, right? Whatever machines they are. Now these, other than where your controller runs on, all of the others would be your compute nodes, and these would receive instructions from the controller saying execute this workload, and they would execute it and then return the results for a job. So this is like a centralized manager that kind of monitors workloads, partitions resources and things like that, and the compute nodes actually handle the job. And we will skip over the rest of the details in the interest of time. And coming to resource utilization, so if you have dedicated nodes, what do I mean by will it do computation? Will what do computation? Sorry, the controller? No, the controller is, well, you can think of all of it as computation, right? But let's say my problem or what I want to do is matrix multiplication. Now will the controller do any part of matrix multiplication? No. It might monitor the workload, it might look at the available cluster resources, it might allocate some resources, it might give this work to those nodes, but it will not do the computation itself. But the things that it does, all the scheduling, is also some form of compute, right? So it's not going to do the actual workload, but it will do the meta work to partition the workload and things like that. So coming to resource utilization, so dedicated nodes, this is very simple, right? Think of your any lab that you have, right? Some CS lab. Now each of you have a lab machine. This is an example of a dedicated node. Now what is the problem here? So let's say you and your lab mate go in different batches and both of you use the same machine, right? Now let's say at some point in time both of you want to use the same machine. So you need to talk to each other and coordinate before you can do this, right? And it might so happen that neither of you use this machine and someone else wants a machine but doesn't have it because their counterpart lab mate is currently using it, right? So with a dedicated assignment system, you always have this issue of resources going wasted, and by design this is not very scalable. If you have 3 machines, you can do this very efficiently. Maybe you talk to all the people involved and figure it out, right? But if you have 1000 machines, this is a lot more difficult to do, right? That's why resource utilization is a challenge. So if you bought 10 machines, then what you care about is that all your 10 machines are being used well, right? That's your resource utilization. Now with a cluster, what happens is that you separate out these two things. Now a user goes to some form of cluster manager and says, I want one machine. Now the cluster manager's duty is to figure out which machine is available, which can I give to this user, and all those other things, right? But as a user, you don't care about all that. You just ask for a machine and you're given a machine. And that's why this leads to both efficient use of resources, because the manager can now go and see, oh, is this machine free? Okay, let me give it to this user. And that way your resources are efficiently used, your resource utilization of the cluster overall goes up, and it is very highly scalable, right? Because now you don't have to talk among the users. All the users simply talk to this cluster manager or resource manager, and there is no coordination involved, right? That's why it's very scalable, and that's the model that is followed now. Okay, so Kubernetes, again we've looked at why containers are a good way of handling applications, and now that you have all these containers, you need to manage these containers that run the applications, so that the container, for whatever reason, if it goes down, you need to automatically start another container, because again, like I was saying in the previous slide, the management is kind of completely separated out from the user, right? Now a user doesn't need to go and figure out that, oh, my container went down, and then manually start another. The system can be smart enough to handle this, right? And this would be more easier for the user, and it would be more useful for the user, right? And that's something that Kubernetes tries to do as a container orchestrator. So again, these are some terminologies, and again you'll find a lot of these terminologies overlapping between different things, right? So in terms of a hardware deployment, you might hear of this word cluster, you might even hear of it in terms of a Kubernetes thing. So it's a very generic term. It can mean different things at different points in time, right? Similarly, the word node, right? So here you might see an explanation that says nodes are the workers, right? Which was different from what I told you earlier. So remember that all of these take meaning with a context. So look at what is the context and then try to understand the meaning. Okay, when I train your model, will I put it in a container and train? Yes, that is something that is commonly done. So one reason is application packaging. So let's say you train using version PyTorch 2.0, right? For whatever reason, PyTorch 2.0 might have a certain feature that you want. Your friend might be training with a very old version of PyTorch, and now there are ways to have both of these installed on the same system, but a good way to do that is a container, right, where your application and all of its dependencies are packaged together. So that's one of the reasons why training is done with a container. Now the second reason can be something like isolation, right? Let's say you have certain training data that you as a company may not want to expose to certain others. For instance, your phone is a good example of this, right? There are different apps that run, and some of these apps might actually be doing training with your data. I think earlier I mentioned federated learning, which is a privacy oriented application that uses your data and trains on the device itself. So for instance, let's say you're typing something on your keyboard, right? Your keyboard tries to learn what you're typing so that it can predict what you're going to type more efficiently. Now there might be other applications running on your phone, right? And you might not want those other applications to actually know what you're typing. For instance, you might not want Amazon to know what you told your friend 5 minutes ago on a WhatsApp chat. Maybe Amazon uses that to give you ads for certain things or all sorts of things, right? So if you use containers, again you get some level of isolation, right? So, and finally you might just use it for multi-tenancy with some form of resource partitioning. So three broad reasons why you would use containers: isolation, application packaging, and multi-tenancy. Okay, so even if the container, hope that's answered your question, feel free to ask follow-up questions. Even if the container has stopped working, the application keeps running, right? In some way we do want something like that. If you look at a lot of cloud service providers, So let's say, look at Gmail for instance, right? You store a bunch of emails on their servers. Now, if let's say, obviously Google does not have hardware that will never fail. They have hardware failures, but you as a user don't want to wake up one day to a message saying, you know, the server that was holding all your emails crashed and all your emails have vanished now. Sorry about this, right? You would never appreciate Google if it did that to you, and you would be so aghast and you would complain about it to everyone, right? So in a way, these failures are kept from the user and they are managed internally. For instance, one thing Google can do is to store 3 copies of your data, and by using this redundancy, they can deal with failures of one particular node or one particular machine. So similarly with containers, what we want to do is, if a container goes down, we want to bring it up without the user even knowing about it, right? That's one of the ideas behind all of this. So I think in one of the crash and the load balancing demos, you probably saw that, right, with the lectures. That's the broad idea, to keep some of these details away from the user, to abstract it away from the user, and still give the user the end goals that they want. All they want is their application keeps running, right? You accomplish that behind the scenes as an orchestrator. Orchestration can be done without containers. For the purposes of this course, we will use orchestration to refer to just containers. Other than that, I have not heard of orchestration be used in a context outside of containers, but it may be possible. I think you should look it up, and if I find a use like that, I will let you know in the next lecture. But broadly, it is used very closely with containers. Okay, how many? We're already at the 8:30 mark, so let's see how much I have left. Okay, I think this is the last one, so I think this is fairly clear, so I will skip this and we will move to the questions. So again, they are very similar to last week. They're all MCQ based, so I would appreciate it if you guys kept it interactive, and it's fine if your answers are wrong. It will help me calibrate my explanations, right? If a bunch of you get an option wrong, I know that there is some confusion with that. So feel free to answer, okay? So a generic ML workflow is as follows, and you have 5 steps. You need to arrange them in the order of the workflow. Look through the options and give me an answer when you are ready. Okay, we have one answer, B. Okay, a lot of people think that it's B. Anyone else? B. Okay, B. Okay, that's great. Everyone seems to think that it's B. It is B. And broadly, the steps are like this. You source and prepare your data, you design your model, you train and you evaluate your model, and then you test your model, and then you deploy it. And that sequence maps to option B. Any doubts or questions on this? If not, let's move to the next question. What does the command docker ps do? And you have 4 options. Take your time and think about it. A, okay, B, C. Okay, we have a lot of answers to this one. I'll wait 10 more seconds. Okay, let's look at the answer. The answer is B, display all running container details only. There is a different command to display all Docker images. PS, if you're familiar with the Linux, so without Docker, if you just go do a PS, it will give you a list of all running processes in Linux, right? And the Docker PS is intended in a very similar sense, right? It gives you all container details. but without an argument. If you use a ps-a, then it would give you all container details. Without the hyphen a, it will give you only the running container details, and the command to display all images is completely different. So I think it's what docker ls, I don't remember, but you can look that up. It's a different command. Okay, let's move to the next question. Docker run -it -gpus all -p, and yeah, docker images. Okay, that was a command probably. And in this command, the -p represents what? That's your question. Okay, port A. Any other answers? A. Anyone else? Okay, let's look at the answer. It is A, port. And one thing I wanted to tell you here is, let's get a cursor, right? So if you're looking at a Linux command for something, right, and you don't know what it is, for instance, I told you about ps, other commands might be ls, a lot of commands you might not know the syntax of. What you can look for is something called a man page, right? It's like a manual for Linux. I think that's what it stands for. So you can either type man ps or man whatever command name in the terminal itself, or you can just Google saying man ps, and that will bring up the manual entry for this. And all or most Linux commands have a lot of command line flags and options, and the manual page is the first and the most reliable source you should be looking at, not other random websites. So that will tell you exactly what the command does, what each of the options do, and so on. Similarly, for Docker and for any third party tool, they would have their own programming manual or command line interface guide or things like that. That is the source that you should go look at. For instance, if you wanted to know what this looks like, I think this is from the Docker user guide. So this tells you -p or --expose, which does the same thing. It publishes or exposes a port. So in this example, for instance, we do docker run -p 127.0.0.1:80:80/tcp. So what this does is it binds port 8080 of the container to the TCP port 80 on 127.0.0.1, which is localhost, right? So this guide will not only give you examples like this, but will also tell you how to use this. Again, not very relevant from this question, but if you're trying to use one of the Docker commands and you're stuck and you don't know what's the right syntax, you should go look at the Docker user guide. It will give you examples and it will tell you how to use it. Docker is based on Linux syntax. Typically yes, because a lot of people are familiar with Linux, and so to keep things easier on that side of things, a lot of commands take origin from there, right? So things like ls, ps, a lot of those commands. But that doesn't mean that you need to learn Linux to understand Docker. You can simply, so when you learn a new tool, a great way is to get a cheat sheet, right? Lots of people who learn new tools make these cheat sheets with the top 20 or 30 commands that you would be using. So if you go look up Docker cheat sheets, you would find 20 or 30 versions of them having all the commands that you need. So you can simply print one of those cheat sheets, put it up on your desk, and you will keep looking at those commands and you will start remembering them. That's a very good way to learn a tool. But in general, I would definitely recommend learning Linux tools and commands as well, because a lot of such things become easier on Linux. And it's okay if you have a Windows based machine, right? So do I. like I said, you can always get a virtual machine and you can set it up with a Linux environment. That will help you because, as you may have seen in this course, a lot of instructors and developers give you the Linux version of things, and you always have to go through this additional step of finding the Windows equivalent, finding the Windows installation procedure, finding the Windows commands and all that, right? So Linux is easier, it's more preferred overall, and so it would be good to learn it, but it's not very necessary just to learn Docker. That's my advice. Hope that helps. Moving on, the most prominent scheduler used in high performance computing and AI is C, Slurm. Anyone else? C. C. A. Okay. Okay, someone also asked about B. Any other answers? Okay, let's look at the answer. It is Slurm. Although of late there is a lot more push towards Kubernetes, Slurm has been around for a lot longer. As you studied, more traditionally it is used in HPC. So, and it still remains to be that for HPC. So C is the right one. PBS, I think, is a portable batch system from Altair, but again Slurm is a lot more popular in the HPC world. So the answer is C. And Kubernetes is kind of getting there. Okay, haven't reached here in your lectures. Isn't Slurm a manager? So let's go back to that slide and take a look at it. So if you look here, right, so here we talk about this scheduling versus orchestration, and then we move on to Slurm. So in fact, even in this slide, the example given is Slurm. So Slurm is a scheduler, and as part of that scheduling, it also includes this controller which does a lot of management functionalities. So one part of Slurm would be to manage workloads and the cluster as such, but broadly it is a scheduler. Okay. Yeah, let's move on. Which command is Kubernetes is an orchestrator, not a scheduler. Yes, but it does include scheduling, right? So you could think of it as a scheduler in a way, but orchestrator is the more correct term. Okay, moving on. Which command is used to check the running batch and interactive jobs by current user? S-info, SQ. Okay, in Kubernetes, does the main controller do computation? Let me see. I think I have a whole bunch of questions to run through today, so I might get to this later in the next lecture. So one option is A. Anyone else? S-info. Again, this tests your recall of these commands, and if you've not used the tool, you might not remember. Okay, A. Anyone else? A. Okay. Let's take a look. So it is SQ-U user, right? So if you want to check the node's status, it is sinfo. If you want to submit an interactive job, it is srun. If you want to check the status of the running job, it is sq. And if you give a -u $user, then it would give you for that current user. So the answer is sq. Which program or application is this? It is the Slurm itself, I think. So this was part of the week 2 lectures, right? Just confirming that some of you at least have seen this. I think there was a demo or something like that about Slurm, and some of these commands were run and shown. Or have none of you seen it? I remember seeing this, and I think I have only gotten to week 2, so it must have been there. Okay, none of you remember. I think it was there. It definitely should have been there, because I think Slurm was introduced and then you had some sort of a demo, right? I think in that demo, yes. So someone has seen it. So make sure you look through. You might have missed a video, or you might have missed part of a video. So maybe go look at the video which talks about Slurm and gives a demo. You should be able to find this. Okay, going to the earlier question, in Kubernetes, does the main controller do the computation? Typically, the controller does not do computation, but I can kind of go a little bit. I think I skipped over the Kubernetes architecture slide, this slide, right? So I can maybe go through that a little more in detail next week if that helps. That way you'll understand more about the control plane and the data plane. Okay, let's move on. Kubernetes is an orchestration tool because here are your options. Okay, we have a few answers saying D. Okay, anyone else? D. Okay, we have a lot of answers saying D. Let's look at the answer. It is D. So it supports scheduling to improve cluster utilization. Yes, it also supports some features that are not typically part of the scheduler, but things like load balancing and auto scaling. And C supports on-prem cluster only is not true. So A and B is basically your right answer. And some of the other features of Kubernetes are here, but we'll skip past that. Next question, Dash can be considered as the primary data store of Kubernetes. etcd. Okay, etcd. Anyone else? Okay, bunch of people think it is etcd. Okay, great. Let's look at the answer. It is etcd. Again, going through some of the terminologies. A pod is the smallest execution unit, right? So it's a single instance of a running process, and nodes in this context are the workers that run the applications. And again, on a node you have multiple components like these. We'll go through some of this in the next lecture. I think we didn't have the time today, but etcd is the primary data store of Kubernetes. Okay, the different services within Kubernetes are cluster IP, node port, load balancer. D, all of the above. D. Anyone else? It is all of the above. All of you guys are right, and I don't think anyone was confused about this. So let's move on. Command to create a .yaml file in Kubernetes, and you have various options. Any answers? All of them look too similar and too confusing. So I think this is one of the problems with courses where you have a lot of hands-on, right? A lot of what you learn is just commands and syntax of commands, which you technically don't need to know to understand the tool or to understand what the tool does. But if you're supposed to ask MCQ questions on those tools, then very often they end up being commands and syntaxes, which is not really a test of how well you understand the tool, but yeah, that's fine. So it's okay if none of you guys remember, or maybe this wasn't even part of the demo, right? Could have well been the case. So the answer is kubectl create -- file name, and then you give the argument, right? Typically things that change, right? So instead of this file name, I could have foo.yaml, or I could have some abc.yaml. That's why you have a flower bracket to indicate that. So this is the syntax, and these are a bit, so if I were you and I didn't know the actual syntax, I would try to guess it, right? So typically this would be my first invalid option. So one way to figure out which is the right answer is to eliminate things, as all of you might already be doing. So this one, for instance, has no argument, right? So it would be an invalid option. This probably would be an invalid option because many times I think these things have a hyphen syntax, or they have a hyphen with a single letter, right? That's again something that's based on observation. So you might see something like -u, or you might see things like -p versus -- expose. So my second guess would be that hyphen file name sounds wrong. So again, I would eliminate that, and then I would probably pick this as my best bet among all of these options. So for some of these questions where you don't know the answers, try to think logically based on syntaxes of commands that you've already seen. And again, you need to pay attention to these small details, right? But in Linux, a lot of these things are not arbitrary. They're not randomly picked. They're very well crafted and very well designed. So a lot of tools will follow the same format. So that's one way of getting to the answer if you don't know. Anyway, let's move on. Deep ops is a dash. Any answers to this? No answers? Is it CPU or GPU or both? No answers? Okay, let's take a look. It is typically a GPU cluster, right? So the word DPOPS itself is used in context of a GPU cluster, because again it comes from deep learning and operations, right? And that typically uses a GPU cluster. So again, think about, if you've not already heard of this, think about the word itself and what it might mean. So again, you might have heard of things like AI ops, ML ops, or DevOps very generically, right? So yeah, again, not a question that tests a lot of your understanding. It's more a terminology question. But with that, I think we are at the end of today's session. We still have 5 minutes left, so that's good. So, any questions or doubts in any of week two's content? It need not be very particular. For instance, it might be, I don't understand the Kubernetes architecture really well. Could we talk a little bit about that? It could be something like that. Feel free to ask that on chat, and I'll definitely come back with something that helps you understand it better in the next session. If you don't have any questions, don't have any doubts, you feel free to drop off. Thank you so much for attending the session. And if you have any feedback on the session structure itself, saying I would like more of so and so, feel free to drop that on chat too. I'll try to do my best to accommodate your requests. And hope this session was useful and helped you understand the course better. Any questions, comments? We have 4 more minutes. Anything that was not clear in week 1 or week 2 that you would like more detail on? Nothing? Okay, then that's good. So thank you so much for attending. Thanks for keeping it very interactive, and look forward to seeing you next week. Thank you. Sure, thanks everyone. Thanks for all the comments, and I will explain Kubernetes also next week. Thank you so much. Yes, please come with questions that would benefit both you and me and everyone else who's listening. Thank you so much. See you next week.